A significant, and constantly increasing, share of the total volume of modern combat training of flight personnel takes place not in real air at all, but on the ground, in specialized, technically extremely advanced simulators, the realism and practical value of which has increased significantly over the past decades. A modern full-featured combat aircraft simulator is a much more complex, technically rich system compared to the relatively simple first generations of similar devices used several decades ago. An accurate, detailed copy of the real cockpit of a specific type of combat aircraft, often installed on a special movable platform, capable of at least partially, to a limited extent, simulating the real physical sensations of overload and vibration during a maneuver performed by a pilot during training, complemented by an extremely realistic, high-quality visual system that surrounds the pilot with an almost complete, panoramic picture of the outside world, including the most reliable simulation of both the real terrain of a specific geographic region, and the behavior of various types of friendly and enemy aircraft in ground objects. The key practical advantage of such a modern, technically advanced training system is the fundamental possibility of the most realistic practical training of an extremely wide range of different combat scenarios and tactical situations, including the most dangerous, critical emergency situations, the training of which in real flight conditions would be either extremely dangerous or simply physically impossible without the real destruction of expensive military equipment and, most importantly, a real risk to the life of the trained pilot. A significant additional practical advantage is the significantly lower relative cost of such ground training compared to the cost of real flight training on a real combat aircraft of similar duration, which requires significant expenditures of expensive aviation fuel, intensive maintenance of real equipment and, importantly, the gradual, inevitable depletion of the structural life of a real aircraft airframe, which we have already discussed in detail in one of the previous parts of this material. Modern training complexes demonstrate particular practical value in relation to the development of complex group tactical interaction. Several separate simulators, often physically located in completely different geographical locations, can be technically combined into a single, common training environment through modern secure communication channels, allowing several different pilots to simultaneously practically practice complex joint tactical interaction within a single, common conditional combat scenario, without the need for the physical joint presence of all participants in such a group training at one common airfield. It is important, however, to emphasize that modern military aviation, despite all the significant progress in the field of technically advanced training systems, does not at all consider such ground training as a full-fledged, comprehensive replacement for real flight practice. Certain aspects of a real flight, including the direct physical sensation of real overload, real psychological stress from the awareness of a genuine, not conditional risk, and a number of other subtle, difficult to formalize aspects of real flight experience, are objectively impossible to be completely, 100% reproduced even within the framework of the most technically advanced modern training system, which makes a reasonable, balanced combination of a significant volume of relatively inexpensive, safe, and very flexible ground training with a mandatory, invariably necessary certain volume of real, practical flight training the optimal, most effective modern approach to the general system of combat training of military flight personnel. We have already examined in detail the modern technique of landing an aircraft on an aircraft carrier using an aero finisher and a hook. But the very design of a modern flight deck, located at a characteristic angle to the longitudinal axis of the ship's hull, is a relatively late historical invention, the appearance of which radically increased the safety of carrier-based aviation and without which modern intensive flight operations on board an aircraft carrier would simply be impossible in their current form. During a fairly significant initial period of development of carrier-based aviation, right up to the 50s of the 20th century, aircraft carriers had a single, straight flight deck, where the takeoff zone and landing zone of aircraft actually coincided with each other, located strictly along the same line along the longitudinal axis of the ship. This design created a very serious, potentially catastrophic safety problem in the event of an unsuccessful landing, when the landing aircraft for some reason failed to hook the hook on any of the arresting cables. It simply had nowhere to go except to crash into other aircraft already parked in the bow of the same straight deck. It was to prevent such catastrophic accidents, unfortunately quite common in practice, on the direct flight decks of early aircraft carriers that a special emergency barrier was used, a barrier that was a strong mesh or cable stretched across the deck behind the parking area of already landed aircraft, designed to physically stop an unsuccessfully landing aircraft before it crashed into the equipment in front, although such an emergency solution in itself often led to serious damage to the unsuccessful aircraft itself and posed a significant risk to its pilot. The revolutionary solution to this fundamental problem was first proposed by British naval specialists and consisted of a rather simple, but extremely effective idea to shift the immediate landing zone of the aircraft relative to the general longitudinal axis of the ship by a certain angle, usually on the order of 9 to 10 degrees, thereby creating, in fact, two functionally independent zones on the same deck, the main, straight part of the deck, used primarily for parking aircraft and operating catapults, and a separate, a corner runway designed specifically to accommodate landing aircraft. Such a seemingly rather simple geometric solution brought a colossal practical effect. In the event of an unsuccessful landing, in which the landing aircraft failed to engage any of the arrestor cables, the pilot now received a real physical opportunity to immediately give full throttle and make a safe, unhindered go-around, since the angular landing strip itself, due to its location shifted relative to the general longitudinal axis of the ship, was no longer physically blocked by aircraft parked in the bow of the main deck, which previously represented a mortal danger. Precisely in similar emergency situation, the introduction of such an angular deck into the design of aircraft carriers in the mid-50s of the 20th century, along with the introduction at approximately the same time of the previously dismantled optical landing system, is considered one of the most important technical achievements in the history of the development of carrier-based aviation, which most directly contributed to a very significant reduction in the overall accident rate and, most importantly, a significant reduction in the number of casualties during the inevitably risky takeoff and landing operations on the relatively limited space of the flight deck of a moving ship. We have already examined in detail the technical structure of the modern vertically taking off version of the EF-35. But long before the advent of such modern technology, back in the 60s of the 20th century, a fundamentally different, revolutionary combat aircraft in its own way took to the air for the first time, which for the first time practically proved the very possibility of full-fledged combat use of a jet aircraft with vertical takeoff and landing, the British Harrier, later, in a modified version of the AB-8B, which was actively used by the American Marine Corps over many subsequent decades. The fundamental technical solution underlying the Harrier's vertical takeoff and landing differs significantly from the previously discussed EF-35 Bravo system, which, as we remember, relies on a combination of a separate lift fan in the front of the fuselage and a rotating main engine nozzle in the rear of the aircraft. Harrier uses a fundamentally different, much more conceptually simpler system, a single, very powerful Rolls-Royce Pegasus turbofan engine, equipped with 4 separate rotating nozzles, located in pairs on both sides of the aircraft fuselage. These rotating nozzles are capable of synchronously turning at an angle from the normal, straight aft position, providing traditional jet thrust for horizontal flight, up to the straight down position, providing the direct vertical lift required for vertical takeoff, hovering in the air or vertical landing. Such a system, for all its conceptual elegance, required exceptional skill and precision control from the pilot, especially during the critical transition period between pure vertical flight and conventional, level wing flight, since it is at this transition point that the aircraft temporarily loses part of the aerodynamic lift provided by a conventional wing at sufficient level flight speed, being forced to rely on the gradually decreasing, but still significant, vertical reaction component of thrust from the rotating engine nozzles gradually unfolding to their normal position. A significant additional technical challenge was ensuring the overall stability of the aircraft directly in hovering mode or slow vertical flight, for which the Harrier design provided a special jet control system through additional small nozzles located at the ends of the wings, in the nose and tail of the fuselage, using compressed air taken from the main engine compressor to create the necessary corrective jet impulses, compensating for the slightest deviations of the aircraft from a stable position immediately hovering, when conventional aerodynamic rudders, effective only when the airflow is at a sufficient speed, become practically useless. The practical tactical value of such a capability for vertical or, which was used much more often in real combat practice, short takeoff from an extremely limited runway, turned out to be extremely high, especially for the Marine Corps, which regularly operates from relatively small landing ships that do not have a full-fledged long takeoff deck of a full-size aircraft carrier, as well as from temporary, hastily equipped field sites in the immediate vicinity of the front line, completely inaccessible to conventional fighters of traditional design, requiring a much longer runway. The experience of creating and many years of practical operation of the Harrier subsequently served as a very valuable, in many ways invaluable practical basis for the developers of a much more technically complex, modern vertical takeoff system of the already mentioned F-35 Bravo, which clearly demonstrated in practice the very fundamental possibility of creating a full-fledged, combat-ready jet fighter capable of effectively combining the traditional high-speed and maneuverable characteristics of a conventional aircraft with the unique ability of vertical takeoff and landing, previously considered the almost exclusive prerogative of helicopters that were much simpler in their aerodynamics. On April 18, 1942, just a few months after the surprise Japanese attack on Pearl Harbor, one of the most daring and technically risky air operations in the entire history of military aviation took place, the famous Doolittle Raid, during which 16 land-based B-25 Mitchell medium bombers, aircraft never originally designed for deck-based operations, successfully took off directly from the flight deck of the aircraft carrier USS Hornet for launching the first symbolic airstrike directly on Japanese territory. The strategic logic of such a very unusual and technically extremely risky operation was dictated, first of all, by the urgent political and moral need to inflict at least some, even relatively limited by purely military standards, but at the same time psychologically extremely significant retaliatory strike directly on Japanese territory soon after the traumatic, demoralizing surprise attack on Pearl Harbor, thereby demonstrating both to its own population and directly to the enemy the real vulnerability of the Japanese metropolis in the face of a potential American retaliation, contrary to the then widespread belief in Japan itself about the complete physical inaccessibility of its own territory to any potential enemy. The key technical problem was that not a single carrier-based bomber existing at that time had a sufficient flight range to carry out such an operation, which required striking Japanese territory from a considerable distance from it, followed by continuing the flight to relatively safe airfields on the territory of Allied China, since the aircraft carrier itself, due to obvious reasons for its own safety, could not afford to approach a distance that was comfortable for action much less long-range standard carrier-based aircraft of that period, close to the well-defended Japanese coast. The solution was to use a fundamentally different type of aircraft, a land-based, twin-engine medium bomber B-25, which had a significantly greater flight range compared to standard carrier-based aircraft of the time, but had never before taken off directly from the flight deck of an aircraft carrier, which was much shorter and objectively much less suitable for the takeoff of such a large and heavy land aircraft compared to its usual long one. Ground runway. The crews selected to participate in such an operation underwent an intensive training program specially developed specifically for this unique task, practicing the shortest takeoff technique, which included specific techniques for making full use of all available engine power already at the very start of the takeoff run, a certain, very non-standard position of the flaps and other aerodynamic elements of the aircraft, as well as precise coordination of the cruise actions in conditions of extremely limited, compared to usual ground practice, available length takeoff run, further complicated by the constant, significant rocking of the very deck of an aircraft carrier moving through a rough ocean. The operation itself was actually carried out under conditions significantly less favorable compared to the original plan. The aircraft carrier group was discovered by a Japanese patrol vessel at a significantly greater distance from the Japanese coast compared to the originally planned, much shorter distance, which forced the command to make a difficult decision to immediately take off the aircraft several hours earlier than the originally planned time and from a much greater distance to the Japanese coast than originally expected, which subsequently significantly complicated the already extremely risky further flight of the majority of the crews participating in the operation to the relatively safe territory of Allied China. Despite the relatively limited direct military, purely destructive effect of the strike itself, the psychological and strategic significance of the Doolittle Raid turned out to be colossal. The operation convincingly demonstrated the fundamental vulnerability of the Japanese metropolis, which subsequently had a significant impact on further strategic decisions of the Japanese military command, and the very fact of the technical feasibility of such a takeoff of a heavy land bomber directly from the relatively short deck of an aircraft carrier, seemingly impossible according to the original technical parameters, remains one of the most striking historical examples of how significantly real military necessity can stimulate the search and practical implementation of non-standard, at first glance technically absolutely impossible engineering and tactical solutions. We have already mentioned the general principle of the existence of two-seat combat aircraft and the distribution of tasks between the pilot and the second crew member. But the specific, official military specialty of such a second crew member, a weapons officer, weapons systems officer, WSO, or, in Navy terminology, a naval observer pilot, naval flight officer, NFO, deserves a separate, more detailed consideration precisely as an independent, highly specialized profession, fundamentally different from the actual piloting of an aircraft. It is important to understand the fundamental difference between such a specialty and a regular pilot. The weapons officer, as a rule, does not have direct access to the main flight controls of the aircraft itself and, with rare exceptions of certain emergency situations, does not directly pilot, focusing instead entirely on a much more highly specialized set of tasks related directly to the effective use of complex onboard weapons and various tactical systems of the aircraft. The specific responsibilities of a weapons officer vary significantly depending on the specific type of aircraft and the nature of the combat mission being performed, but, as a rule, include the detailed control of the complex onboard radar system of the aircraft, the various technical aspects of which we have already discussed in detail earlier, including the accurate identification and subsequent tracking of potential targets, the management of the previously mentioned sighting containers, and the associated process of precision target designation, the detailed planning and subsequent coordination of the direct use of various types of airborne weapons, as well as, in certain types of combat missions, direct coordination with other aircraft of the group or ground units, including the previously discussed coordination with ground JTSE gunners. This functional distribution of tasks between the pilot, who is completely focused directly on piloting technique and general situational awareness of the surrounding air environment, and the weapons officer, who is responsible for the much more highly specialized, but at the same time extremely technically complex set of tasks of using onboard weapons, significantly increases the overall combat effectiveness of such a two-seat crew compared to a hypothetical situation in which a single person would be forced to simultaneously cope with the entire complex of extremely diverse, requiring full attention tasks in conditions of a real, often very fleeting and intense combat mission. The training of a weapons officer, while fundamentally different from the training of the pilot itself, nevertheless also includes a fairly significant amount of actual flight training, providing the necessary basic understanding of the real flight characteristics and limitations of a particular type of aircraft, as well as the ability, under certain, mainly emergency circumstances, to provide the pilot with the necessary assistance or, in the most extreme case, to assume certain basic piloting functions, although such a scenario is considered exclusively as extremely unlikely, purely emergency situation, and not at all as a standard, everyday practice of distributing responsibilities between members of such a two-seater crew. Many years of experience in effective tactical interaction between a specific pilot and a specific weapons officer, regularly flying together as part of the same permanent crew of a certain type of two-seat combat aircraft, often leads to the formation of an exceptionally high level of mutual, almost intuitive understanding and coordination of the actions of such a pair, significantly increasing the overall combat effectiveness of the crew compared to the situation of a random, one-time formation of such a pair immediately before a specific combat mission, which further emphasizes the importance of such a highly specialized, but a military profession that is extremely important for the overall combat effectiveness of modern tactical aviation, often remaining much less noticeable to the general public compared to the more recognizable, publicly much more often mentioned figure of the combat aircraft pilot himself. We have already examined in detail the technical design of a radar exposure warning system, capable of recognizing a specific type of detected enemy radar by the nature of the received radar signal. But such an ability to accurately recognize a specific type of threat is fundamentally impossible without the aircraft having a pre-prepared, detailed database of characteristic technical parameters of all potentially relevant types of enemy radar and other electronic systems, the so-called threat library, or, in more official terminology, a mission intelligence file, mission data file. Such a threat library is an extremely detailed, regularly updated electronic database containing the exact technical parameters of signals from a huge number of different types of radars, communications systems, and other sources of electromagnetic radiation that an aircraft could potentially encounter during an actual combat mission in a specific geographic region or against a specific enemy. The formation and subsequent regular updating of such a critically important database is a separate, very labor-intensive and technically complex area of military intelligence activity, combining data obtained from a number of different sources, previously discussed in detail signal reconnaissance carried out by specialized aircraft like the RS-135, data received from specialized ground-based electronic intelligence stations, the results of a detailed technical analysis of enemy equipment samples that come into possession intelligence services in various ways, as well as a significant amount of analytical work on systematization and subsequent interpretation of all such disparate information into a single, holistic and, most importantly, the most up-to-date database. The critical importance of the maximum relevance of such a library of threats is due to the fact that the enemy, naturally, is not at all interested in maintaining unchanged technical parameters of its own radar and other electronic systems, regular modernization, changes in specific operating parameters, or even relatively small technical improvements to the existing enemy air defense systems can make an outdated, insufficiently up-to-date threat library partially or completely ineffective, potentially leading to incorrect identification of the real type and, accordingly, the level of danger of a specific detected threat by the aircraft's onboard system. That is why updating such a critical database is a constant, ongoing process, and the specific mission data files themselves, downloaded directly into the onboard system of a particular aircraft before performing a specific combat mission, are usually regularly, often very frequently updated, reflecting the latest available intelligence information about the real, current characteristics of the air defense systems of a specific enemy relevant to a given combat mission. A significant additional aspect is the fact that different versions of such a library of threats, as a rule, are developed separately for different potential theaters of military operations and different categories of potential adversary, since the specific set of actual, really threatening air defense systems can vary quite significantly depending on the specific geographic region and the specific, actual adversary against which this specific combat mission is being directly prepared. The importance of such reconnaissance and analytical work, which is largely invisible to the general public, on the formation and constant maintenance of the relevance of a threat library often remains significantly underestimated in comparison with the much more visible, visual technical characteristics of the combat aircraft itself or its onboard weapons, but it is on the quality and relevance of such a database that the real efficiency of the entire complex of onboard aircraft systems responsible for timely detection, accurate identification, and subsequent effectively countering real threats that an aircraft may encounter during a specific combat mission in real, current conditions of a modern armed conflict. In a situation of a serious emergency malfunction over a significant expanse of water, when the possibility of a safe ejection for some reason is unavailable or undesirable, and reaching the nearest suitable airfield for landing is objectively impossible, the crew of a military aircraft may be forced to perform an extremely risky, technically complex emergency procedure, splashdown, ditching, a forced landing of the aircraft directly on an open water surface. Such a procedure is fundamentally different from the usual landing on a hard runway in a number of very significant technical and physical features that significantly increase the overall level of risk for the crew, even with a technically competent, most careful landing itself. The first significant difficulty lies in the very unpredictable, often very unfavorable interaction of the aircraft fuselage structure with the water surface at the moment of direct contact. Unlike a relatively flat, predictable hard runway, the water surface, especially in the presence of even relatively small waves, presents a significantly less predictable, potentially very uneven contact surface, capable of causing severe, often asymmetrical mechanical stresses on the fuselage structure at the moment of initial contact with the water, significantly different from the much more predictable and uniform loads characteristic of a conventional landing on a hard runway. A significant additional complexity is created by the very specificity of the movement of a heavy object, such as an airplane, on the water surface immediately after the initial contact, in contrast to the relatively predictable braking on a hard runway using traditional wheel brakes. An airplane splashed down on a water surface experiences much less predictable, often very uneven water resistance, which can cause sharp, difficult to predict turns or even partial destruction of the fuselage structure if maintaining the optimal angle and speed of initial contact with the water surface. The crews of military aircraft that regularly perform long flights over large expanses of water, primarily maritime patrol and anti-submarine aircraft, as well as a significant part of carrier-based aircraft, undergo mandatory, regularly repeated specialized training for precisely this extremely risky, but at the same time statistically relatively infrequent emergency procedure, including both theoretical training regarding the optimal technique for splashing down a particular type of aircraft, and, no less it is important to practice the subsequent quick, safe evacuation of the crew directly from an already splashed down, potentially quickly sinking aircraft. Considerable attention within the framework of such specialized training is paid to the rapid, most effective evacuation of the crew immediately after the very moment of splashdown, since most types of aircraft, which were not objectively designed initially for a long stay afloat, begin to submerge quite quickly, often within a matter of minutes, underwater after the very moment of splashdown, which makes the time factor critical to ensuring the real survival of the crew in such an emergency situation. That is why the crew's life-saving equipment, which we have already discussed in detail earlier, traditionally includes a certain set of elements specifically designed specifically for such an emergency splashdown scenario: compact inflatable life jackets for individual use, and on certain types of larger aircraft and helicopters also larger, group inflatable life rafts, automatically or manually activated directly at the time of such an emergency situation, providing the crew with a real, practical chance of successful survival in the open air. Water until the arrival of rescue forces, the detailed organization of whose work we also spoke in detail in one of the previous parts of this material. We have already examined in detail the general process of testing new aircraft weapons at specialized testing grounds. But there is a special, rather unusual category of test targets, significantly superior in its realism to any traditional, specially designed towed targets, full-scale, fully flying jet fighters, previously in combat service, but subsequently, after decommissioning, specially converted for completely unmanned, remotely controlled flight, known under the general designation QF, in particular, in relation to the once widely known F-4 fighter Phantom, converted in a similar way to the QF-4 variant. The key practical value of such full-size, fully realistic flying targets lies in the exceptionally high degree of reliability of tests conducted with them compared to the much less realistic traditional test targets. A new air-to-air missile or air defense system, initially developed specifically to destroy real, full-size enemy combat aircraft, can be tested against a truly realistic, full-size target that actually demonstrates authentic, physically reliable radar, infrared and visual signatures of a real combat aircraft, instead of the much less perfect imitation of such characteristics characteristic of specially manufactured, much simpler and cheaper smaller targets. The technical process of converting a decommissioned combat fighter into a completely unmanned flying target includes the installation of a special remote control complex capable of completely replacing all the necessary functions of a real pilot, from basic piloting of the aircraft throughout the test flight up to the execution of certain, pre-programmed or operator-controlled evasive maneuvers in real time from the ground, most realistically simulating the behavior of a real enemy fighter, actively trying to evade the weapon being used against it. Weapons being tested. An important technical and, importantly, economic aspect of the use of such full-size flying targets is the fundamental possibility of their safe return to base and subsequent reuse in the event that the weapon used against them during a particular test missed or, due to certain conditions preset in the test program, was deliberately not used to kill, which allows you to significantly rationalize the overall costs of such very expensive test programs compared to the hypothetical alternative of completely disposable use of such realistic, full-size target on any given trial. However, a significant part of such tests, especially within the framework of the final, most realistic stages of testing new military weapons, still involve the real, complete destruction of the tested full-size flying target directly during a specific test, which is a necessary, objectively inevitable condition for obtaining the most reliable, practically applicable data on the real combat effectiveness of the new weapons being tested against a real, full-size air target. This practice of using historical, once widely used combat aircraft in a similar, very unusual quality of flying test targets evokes in many veterans and military aviation enthusiasts certain mixed, often very nostalgic feelings, since aircraft that were once the advanced military equipment of their time and, perhaps, participated in real combat operations, complete their long operational journey precisely in such a quality, nevertheless providing critically important, objectively a necessary, practical contribution to the further improvement and increase in real combat effectiveness of the much more modern generation of aircraft weapons that are replacing them. We have already examined in detail the general principles of operation of electronic warfare systems, including the fundamental difference between barrage jamming and deception jamming. But this area of military technology continues to actively develop, and the modern American Next Generation Jammer program, the next generation of jamming station, clearly demonstrates the specific direction of such ongoing technological improvement. The previous generation of jamming stations, installed, in particular, on the previously mentioned specialized aircraft A-18 Growler, for all its practical efficiency, was based on technology whose fundamental principles dated back to the 70s and 80s of the 20th century, which, with all subsequent private technical improvements, imposed certain fundamental limitations on the overall flexibility and effectiveness of such a system, which was largely outdated in its basic architecture against a much more advanced one. Technically advanced, modern air defense systems of a potential enemy, actively developed over the next decades. The key technical innovation of the new jamming station is the transition from the previous technology based on relatively traditional, mechanically or electronically controlled antennas to the much more technically advanced technology of active phased array antennas, similar, in many respects, to that used in the most modern airborne radars, the operating principle of which we have already mentioned in one of the previous parts of this material. This technology allows for much more flexible, dynamic, and precise control of the generated electromagnetic radiation, providing the ability to simultaneously set up several fundamentally different, independent types of interference, directed in different directions against several threats of different types and nature, while at the same time significantly more effectively focusing all available radiation power directly on a specific, priority target, instead of the much less effective, more diffuse radiation characteristic of the previous generation of such systems. A significant additional technical advantage is the significantly increased ability of such a new system to more quickly, flexibly adapt to the constantly changing, improving characteristics of modern enemy radar systems, including the previously mentioned ability to quickly change the operating frequency, which significantly complicates the effective use against such technically advanced systems of much less flexible, previous generations of jamming stations. The development and subsequent practical implementation of such a technically much more advanced electronic warfare system clearly demonstrates the general, constantly ongoing technological race between constantly improving detection and destruction systems, on the one hand, and constantly improving systems for countering such threats, on the other hand, a race that, as we have repeatedly noted throughout this material in relation to the most various aspects of military aviation, objectively, does not have any final, once-and-for-all achieved solution, but requires constant, unceasing technological development of both opposing sides of such a permanent technological confrontation. We have already mentioned the general concept of future sixth-generation fighters, which involves close tactical interaction between a manned fighter and several autonomous unmanned wingmen. But this concept, known in general terms as the loyal wingman, is already being actively implemented today within the framework of very specific, real experimental programs, the most famous of which is the American XQ-58 Valkyrie unmanned vehicle. In contrast to previously discussed traditional attack drones like the MQ-9 Reaper, which were initially developed primarily for relatively long reconnaissance and strike missions against relatively weakly protected ground targets in the absence of serious air opposition, the concept of a faithful wingman assumes a fundamentally different nature of practical combat use, joint, closely coordinated actions of a relatively inexpensive, largely expendable unmanned vehicle directly together with a manned fighter in the conditions full-fledged, potentially high-intensity air combat against a technically advanced, modern enemy. The key tactical idea is that such a relatively inexpensive, largely autonomous unmanned vehicle could assume a certain part of the most dangerous, risky functions during air combat, previously performed exclusively by a much more expensive and, most importantly, manned fighter, thereby significantly reducing the real risk to the human life of the pilot while maintaining, and often significantly increasing, the overall combat effectiveness of the entire tactical group as a whole. The specific practical roles that such an unmanned wingman is capable of performing within a joint tactical group are very diverse, from the relatively passive role of an additional, distributed sensor, significantly expanding the overall area of radar and other electronic surveillance of the entire group without the need to unmask the actual piloted fighter by turning on its own onboard radar, to the much more active role of the direct carrier of additional weapons, significantly increasing the total ammunition available to the tactical group as a whole, up to the potential the role of a kind of deliberate bait capable of diverting the enemy's attention and, accordingly, fire weapons, thereby protecting a much more valuable manned fighter. A significant technical and, importantly, financial advantage of such a concept is the fundamental possibility of creating such an unmanned wingman at a significantly lower relative cost compared to a full-fledged manned fighter. Since the design of an unmanned vehicle does not objectively require the inclusion of a significant part of the very expensive life support and safety systems for a human pilot required on a manned aircraft, which theoretically allows military departments to have a significantly larger total number of such unmanned wingmen compared to the inevitably much more limited number available expensive manned fighters. It is important to emphasize that such experimental programs, including the already mentioned Valkyrie, today are still at a relatively early stage of practical development and testing, and a number of significant technical, tactical, and organizational issues, including the acceptable level of real autonomy of such unmanned vehicles in a rapidly changing, stressful combat situation, the reliability and security of communication channels between a manned fighter and such unmanned wingmen in conditions of active electronic countermeasures from the enemy, which we have already discussed in detail earlier, as well as fundamental questions of the permissible degree of autonomy of decision-making by such an unmanned vehicle regarding the possible use of on-board weapons, remain the subject of active, ongoing research and practical tests, the results of which, without a doubt, will have a significant impact on the entire future appearance of the next generation of fighter aircraft. Each new part of this material only confirms what was obvious from the very beginning: the topic of military aviation is truly inexhaustible, and behind each story already told there invariably hides the next one, waiting in the wings.